Good morning. I hope you enjoyed the talk yesterday. The demo was a surprise. I saved the demo after the talk for a surprise. You didn't hear about the demo? Massive outage, flights canceled. One company pushed a security update. The whole world came down. There was the demo. At the end of the talk, I reached into my phone, pushed a button, poof. That was the demo. The timing could not have been better. Okay, this is today our last day, and we're going to start with a talk by Antti. How do you pronounce your name? Kuusisto?
Yes.
Okay, Kuusisto.
Pretty good.
No, but the two, Kuusisto, long U, okay.
Yes.
Descriptive complexity for distributed computing and neural network. Please.
All right. Thank you. This is indeed about descriptive complexity of distributed computing and neural networks, and these are very, very, very related topics. So let me start with some background. So I'm going to just go through some papers that are recent in this topic and not talk about the technicalities yet. The technicalities will come later. All right, so descriptive complexity of graph neural networks was pretty much pioneered by this paper by Barcelo and others. And they characterize a class of graph neural networks, GNNs, in restriction to first-order definable properties. So here is this restriction to first-order definable properties via two logics. First one of them is FOC2. So this is first-order logic with two variables and counting quantifiers. And this works in the scenario where we have global readouts. They are sort of message passing mechanisms where the nodes of the graph can communicate globally, not only to their neighbors as usual in graph neural networks. And without global readouts, the characterization is graded model logic. Then there's another paper by Grohe that I'm mentioning here. It characterizes a class of GNNs, graph neural networks, via guarded fragment plus counting quantifiers plus built-in relations. All right? And there are other papers, but here, both of these papers restrict to constant time GNNs. This means graph neural networks where we have a graph and the nodes are communicating to each other, but there's only a finite number of these communication rounds, or a constant number to be exact. So that's why constant time. Yes. There's very little work on non-constant time or recurrent graph neural networks, but there is this paper from this year in AAAI where these recurrent graph neural networks are characterized, and this is in restriction to so-called log MMFP definable properties. So in restriction to those properties, the characterization is based on the graded model mu calculus. So the counting model mu calculus. This logic is defined for the purpose of the paper. So it's basically similar to fixed point logic of first order logic, where we iterate over monotone formulas, and the iterated variable is unary. But there are no syntactic restrictions like usually in the, for example, LFP, least fixed point logic, where we guarantee monotonicity by allowing only positive occurrences of these iterated variables. Here we simply take any monotone formula. This means that the syntax is not decidable, and the authors do note this. Anyway. Then descriptive complexity of distributed computing, not as well-known a field, but has been started a little earlier. So the first paper, I think, is a paper by Hella and co-authors. I'm one of the authors there as well. And there we characterize, again, constant time distributed automata classes via modal logics. I'm going to define distributed automata and graph neural networks and all those in a minute, but first let's just look at the background. Again, this constant time issue appears here. And this is lifted in a later paper where I lift these characterizations to recurrent non-constant time distributed automata. And the characterizing logic is something called modal substitution calculus. So it's based on modal equation systems that can be then iterated. But there are no monotonicity requirements as usual in these recursion-based modal logics. So we're going to define the logic in a bit. Okay, so let's start from the very basics. Classical computing goes like this. Here we are computing, I think, is it the vertex cover, probably. So we have a problem instance, a graph, say. We turn it into an input string. We use a computer on the string. We get an output string, and that represents a solution. So the solution here is the red subset. So we are here solving a node problem. We are finding a suitable solution set. Distributed computing is a bit different. There, the problem instance is the solving network or computer network is actually the solution device itself. So we have a problem instance. We turn it into a computer network or a network of nodes or neurons or whatever you want to think of these individual nodes in the network. They send messages to each other and update their states. Ultimately, they produce these local outputs, and these local outputs are then the solution to this problem. All right. So let's define this formally. A distributed system is defined as a labeled directed graph where we have a domain, W, a binary relation, and then some unary relations. If you want to think of it as a cryptic structure, you can. I mean, that's how I think of it. And then there's also an automaton, A. And this is a distributed automaton. I'm going to define it in a second. So each node contains a copy of the same automaton. So basically, the nodes are computing and sending messages to each other. And the binary relation is a collection of communication channels. So you send your messages through those arrows in the binary relation. And the predicates that correspond to subsets of the domain, they encode a local input at each node in the usual way. So the ith input bit of node W is 1 if and only if W is in PI. This is the usual way of encoding bits by proposition symbols or predicate symbols, if you like to think of it that way. And we could allow for more communication channels here, and all the results that I'm going to talk about would generalize just like that, including the ones that correspond to graph neural networks. But for simplicity, I'm only going to discuss a single binary relation here. Okay, and then the computation, that proceeds in synchronous steps. So in a single step, each machine receives messages from its neighbors and sends messages to its neighbors. And the messages are actually just the state of the automata, because that's more general. I mean, of course, we could use the state to compute some message and then send only the message, but it's sufficient to simply send all of the state, and that makes things simpler. And then you update your own state based on your previous state and the messages you obtained, meaning the previous states of your neighbors, right? Yeah, every node has the same automaton. Yeah. Yes, state refers to the states in the automaton. Yes, yes. Alphabet. Yeah. Because I guess you're talking about the proposition symbols. I mean, that's.
The automaton reads something. Each automaton in each node reads something. What does it read?
Yes, I'm going to do this even more formally. So, but in round 0, you read your proposition symbols, and in subsequent rounds, you read your own state and the states of your neighbors.
So the alphabet is the power set of the states.
Yeah, okay, those are the possible local, that's the number of possible local input strings, right? But this everything is formal here, I think. So the automaton is a tuple with a set of states, and that's finite. And two functions. Pi is an initialization function, and delta then is a transition function. All right, so we have a finite number of states, and at each node, in the very beginning, you look at the proposition symbols true at that node, and thereby you determine the starting state at that node. So different nodes may have different starting states. Okay? So this is the very beginning. And from there on, you will only use this delta, the transition function. So delta gives each node a new state, or each automaton node pair, to be exact, a new state. And this is computed by looking at your previous state and the set of states of your neighbors. Right. And delta is any function on these with these parameters here. Right. Yes, that's possible. And that's actually one choice, and I'm going to discuss it today. Multisets is more or less the choice of what happens in graph neural networks. Yeah, you could put multisets here. Why not? Yes, there are no IDs or anything like that, but even that case has been considered in relation to logic. But I'm not going to talk about these IDs. These are just anonymous in that sense. And then you single out a set F of accepting states, right? And roughly a node accepts if it visits some accepting state at some stage of the computation, right? So a little more formally. So each communication round is basically a labeling of the domain of your distributed system by states, okay? And the first labeling is obtained by looking at this initialization function that simply reads the proposition symbols. And now, if we define Q prime to be the set of states realized by the neighbors of our node W, then the n plus first label at W is computed by delta. That takes as input your previous state at W, and then the set, not multiset, but set here of your neighbor's state. And strictly speaking here, neighbors mean out neighbors. This is just a convention. This means that the messages or states are sent from the heads of arrows to the tails. That's kind of maybe not the way you would like it to be, but you can easily reverse it. You can easily reverse it if you want. The only reason I choose this convention here is that I want to use modal logics here. And if I chose the opposite convention here, I would have to use modal logics that have only these backwards-looking modalities. And I don't want that. So that's why this convention here. But this is just harmless, right? And finally, a node accepts if its state belongs to the set of accepting states in some round. But note, even if you accept, you don't stop computing. You still keep helping your friends and sending messages, right? It's a very, very basic model of distributed computing. So essentially, the automaton therefore simply computes a subset of the set of states of the set of nodes in the distributed system. So this is according to the example that we saw. You have your network, and then the output set is here, the red nodes, right? So we are talking about node problems here. You may want to consider also graph problems where you simply output yes or no with an input graph. And that is kind of included in what I'm going to talk about today, but for simplicity, I'm just going to talk about node problems. Graph problems could be encoded, for example, such that a graph is accepted if and only if every node accepts, or something like that. But I'm not going to talk about that just for the sake of simplicity. We are simply computing subsets of graphs. All right, so these automata are called finite message passing automata, or FMPAs.
You say that when an automaton accepts, it goes on computing. So it means that the computation goes on forever? Or is there a notion when you stop computing and you say that, oh, those nodes are 1 and the other are 0?
Well, yeah, okay. So here we just want to keep the model simple. Of course, if you are in a finite graph, you will reach an attractor and it will start repeating at some point. So forever, yes. I mean, but in this model, yes, you do compute forever.
But
yes.
If you go to the previous slide.
Yeah.
So when is that you stop and you say that the red nodes are those, and then?
Well, mathematically after omega steps.
Okay.
Yes, but of course, if you want to really do it in reality, you can impose all kinds of conditions. You can even just, accept only some very, very, very mild number of states that, iteration steps, communication steps that you allow. Maybe computed from the size of the input graph or something like that. So you can put a lot of other stuff on top of this.
Okay, but in general, it's an infinite computation.
Yeah. In this general setting, you just go for omega rounds.
Thank you.
Yeah.
At the beginning of your talk, you mentioned this work on constant time. This would mean that there is a fixed bound for these functions fn on the previous slide. And then you look what happens until then. Okay.
Yeah, constant time would be, for example, that is 5, and then you stop, no matter what, no matter the size of the graph, and yes. So it's a very, very, very kind of a very restricted model. Right. You can also allow the state space to be infinite, and delta then can be any function. Doesn't even have to be computable. This is not uncommon in distributed computing because you are really interested in just the network topology issues, not so much computability. But you can impose all kinds of restrictions on MPAs. But MPA here means that the state space is allowed to be infinite and delta doesn't have to be computable. Right. All right, we need to find a logic to characterize this. And mu calculus is not going to do the job. So we need something else. And this is going to be modal substitution calculus. And it's easiest to define it just by using an example. So MSC, or modal substitution calculus, consists of programs. All right. And a program is based on 2 lists of rules. And the lists have the same length or the same number of rules, both lists. Here, n. And on the left here, you have base rules. They are kind of the basis of your induction or computation or whatever you want to think of it. And then on the right, you have induction rules, right? And there's a bit of a difference in the syntax of the base rules and the induction rules. So on the left of each rule, you have this so-called head predicate. That corresponds to, it's interpreted as a subset of the domain of your model. So it's kind of a monadic second-order variable, if you like. But the right-hand side, called the body of the rule, is a formula of modal logic with no restrictions, just a formula of modal logic. But when you look at the induction rules, the body is actually a formula of modal logic that can use, in addition to proposition symbols, it can use these head predicate variables. Now that's the only difference. You can use variable symbols in induction rules, in the bodies, and in the base rules you can't. But there are no monotonicity requirements or anything like this. So negations, you can throw them where you like, and so on. N can be any finite number. So yeah. No. It's just a part of the syntax. It could be 5, 6, 7, 8. Yeah. And of course, you can use these kinds of modal equations also to define mu calculus if you want in a certain way. So now let's give it a semantics. So here's a generic program. And let's define these so-called iteration formulas. So I'm going to give a very syntax-based semantics here. There are other ways to give this semantics. Basically, what happens intuitively is that you have these head predicates, these n head predicates. So that corresponds to n sets over the domain. So you're basically moving n sets around the domain. And that's it. That's what happens. But to give it a formal semantics, let's do it this way. Yeah.
The n at the top and the n at the middle is not the same n, right?
Which ones?
You have n variables, and now you're talking about xi to the power of n plus 1.
Yeah.
It's a different n, right?
Yeah. I should have used a different. Yeah. That. Yeah. Sorry about that. Yeah. Yeah. This is just an iterator here. This is kind of a fixed n. Anyway, so the 0th iteration formula for xi is simply the body of the base rule of xi. So that's a modal formula. It doesn't have variable symbols anymore. Then the n plus first, or maybe I should say m plus first, iteration formula of xi is obtained from the body of the induction rule of xi by replacing all the head symbols in the body, each xj in the body, by the corresponding iteration formula from the previous round. Again, you end up with a modal logic formula without any variable symbols. So this is a very syntactic way to give the semantics, but yes. So everything is unlimited in the sense of that you can use the unlimited syntax here in the bodies. Right. And a node satisfies the program if and only if it satisfies the nth iteration formula for some n of x1. So x1 is going to be kind of a flag or a designated variable or something like that. Otherwise, you would simply be computing, but you want to accept as well, or something like that. So you need to define truth by defining a flag variable.
Question? Aren't you essentially putting in inflationary semantics by saying that it just has to be true sometimes? Essentially, you're making it into inflationary semantics. No?
Yes, I wonder if that's the case. I mean, if you're talking about an inflationary fixed point, I don't see that happening here because I'm not computing a fixed point.
Because you said that it has to happen eventually, sometime for some stage. You're kind of, it is almost as if you're accumulating all the stages, no?
Could be. I can't answer that. I don't know. I don't know if that's. Okay. I would have to. Yeah, that's true. It's
inflationary, not mono. I didn't say it's inflationary semantics. It doesn't have to be monotone. It's just cumulative. It's not quite because you're not putting the accumulation inside the semantics.
Indeed, that's the problem. I'm not putting it. So the sets could be flipping.
Accumulation inside the semantics. Okay, yeah, that's a difference.
Yeah.
You're putting the accumulation outside rather than inside.
Yeah.
Okay.
Yeah. Right. And just for those who don't know modal logic, diamond phi means that some out neighbor satisfies phi. So basically, diamond phi is saying that there's a neighbor that could send me the information phi. That's the intuition here. All right. Theorem is modal substitution calculus precisely captures FMPAs, so finite message passing automata. So it's the right logic for this stuff. And we can say something about MPAs as well. So co-theories of model logic are precisely as expressive as MPAs. So co-theory is just an infinite disjunction for us. But you can use this also as a characterization of theories of model logic if you like. So they complements of theory definable pointed model classes, right? Okay, this MSC model substitution calculus is orthogonal in expressivity in relation to MSO, monadic second-order logic. And of course, I can't prove it now because of the time constraints, but I can kind of give you some intuition. So because MSC is synchronized, you can easily define this so-called center point property. That's a node property, and it says that, yes, orthogonal. Yeah, incomparable. Each logic can define a property that the other logic cannot. Yeah. So neither is contained in the other. So the center point property says that no matter how you walk and where you walk, if you take a directed walk, in case steps, you will end up in a dead end, right? And that's easily definable in MSC. And it's easy to show by an Ehrenfreund-Freiseg game argument that you can't do it in MSO because MSO cannot count the lengths of paths very well. So ultimately, well, it can count all kinds of periodicity properties and that stuff, but can't really count lengths of paths because you can start pumping them. And on the other hand, MSC cannot even define non-reachability. And this is something that is kind of paradigmatic to many models of distributed computing. Let me try to explain why this holds. So if you're doing distributed computing, you're sitting at the node. You're simply receiving messages from your friends, and you don't know what size your graph is. So in order to know that some property P, for example, proposition simple P, is not reachable, so you can't reach a node that satisfies P, you would have to sit there forever, and then you would know, okay, it's not reachable. But acceptance here has to be kind of finitary in the sense that at some point you must know if you are going to accept. So non-reachability, it's not possible because you would have to kind of wait forever. Reachability, on the other hand, is easy to define here. All right, the satisfiability problem of the one variable fragment is B space complete. So what is the one variable fragment? You can use only one head predicate. And already this one variable fragment can define this center point property, so it's orthogonal with MSO. On the other hand, MSC contains the mu fragment of the model mu calculus. So what is the mu fragment? If you put the model mu calculus formally into negation normal form and you disallow the greatest fixed point operator, that's the mu fragment. Right. A few more results before we move on to neural networks. So an FMPA whose transitions are independent of the current state is called forgetful. So this means that the transitions don't care about your current state. They care about only the messages that they receive, right? So they kind of forget about their own state. And the class of forgetful FMPAs, if you consider them on word models, I'm not going to formally define what word models are, but anyway, if you do that, they are equi-expressive with MSO. So that's kind of nice. But on trees, FMPAs are more expressive than MSO. And the emptiness problem for forgetful FMPAs on all graphs is in log space. That's pretty low. And for general FMPAs, it's undecidable. Why is that? Because FMPAs are not that different from cellular automata. In a sense, we are talking about cellular automata on general networks. And it's well known that with cellular automata, you can simulate Turing machines.
What about, for example, forgetful FMPAs on trees?
Sorry?
What about forgetful FMPAs on trees? Is the satisfiability problem, the emptiness problem, decidable?
I don't think anybody's considered that. So
Right, MSO, this is a celebrated result. MSO decidable on trees.
yes,
This formalism decidable on trees.
yeah, I don't know, but this is not celebrated. But yeah, it's an interesting question. I really never had time to think about this. Yes.
Yes. I mean, because MSO is equivalent to tree automata. That tells you that forgetful FMPAs is more powerful than tree automata.
Yes, indeed. Yes. Yes, indeed. I mean, it would be interesting to look into this, but I've never given a second of thought to that.
My conjecture would be undecidable.
Yes, perhaps. Graph neural networks. These are not so different from distributed automata. They are basically, to me, they are just distributed automata that compute with feature vectors. That means vectors of reals. Okay. So some notation first. Let mult S denote the set of multisets over S. And define some fixed set of proposition symbols.
Just a quick question. If you had taken before for this automata message passing, so if you're using the power set, you use mult. Would it change expressive power? Just take the previous definition,
Yeah,
but use mult instead of power set.
indeed.
Would it change expressive power?
It will, because this is basic MSC is bisimulation invariant, and with multisets you can say that you have two successors that satisfy. Okay. So even in the constant time case, it will. Yes.
Okay.
And actually, we are going to go to that model in a second.
Okay.
Yes. All right. So we fix some set of proposition symbols, and then we fix D. D is going to be the dimension of our vectors of real numbers. So recurrent graph neural network is a tuple like this, where you have an initialization function, transition function, and again, we will put this set of accepting feature vectors. And we compute in a label-directed graph, just as before. And this goes as follows. So the initialization function just looks at the label symbols or proposition symbols true at the node and gives you a feature vector at that node. That's kind of the first state at your node, if you like to think about that in that way. I call it here the initial feature vector. Okay. And then in subsequent rounds, you update. That means you compute a new feature vector. And this is computed in this way. So let's see what this does from the inside out. So first you look at the multiset of feature vectors in your out neighbors. Okay. Then you somehow aggregate them. It would be paradigmatic simply to sum over them, because sums over sets are, of course, these kinds of multi-set operations. This means you get a feature vector here, and as a first input here, you have your previous own feature vector. Then you combine them just using some combination function. Okay. So on this level, there are no restrictions on these functions. They could be very uncomputable and all that, but we are going to make some assumptions about them a bit later. First, let's define graph neural networks with floats. So they are exactly as we defined in the previous slide, but now we use floating point numbers. And for aggregation, we use the sum, just the sum. We could put here other functions, but I want to keep it simple, so it's the sum. Then simple GNNFs are very specific kinds of GNFs that have this kind of a definition. I'm going to go through it, but it's not very important what the details are. The point is that when we translate from logic to GNNs, because we want to characterize GNNs with the logic, we want to translate to as kind of a weak and simple model of GNNs as possible to get a better result. So that's why we define these simple GNFs, right? And the specifics of the definition are not that important, but they are basically just taken from the model of Barcelo and others. Even though here they use reals, but we take the same model and use floats. So here the aggregation is simply kind of a sum over the feature vectors of your neighbors, but just for some reason you use a matrix to those feature vectors first for some generality. I think you could use here an identity matrix as well. You would still get our characteristics. Yes.
Don't they allow to change the dimension of the features at intermediate layers?
No, yeah. Notice that here we are talking about the recurrent graph neural network. Yeah, yeah, yes. All right, so you somehow aggregate the feature vectors of your neighbors. Then you take into account your own feature vector. Again, just for fun, you multiply it by some matrix, but you could also here use identity. And then you have this bias feature vector. You add it. Then you need a nonlinearity function here, f. And here it's the pointwise applied truncated ReLU. So this function that looks like the ReLU but doesn't give you greater outputs than 1, right? All right. Anyway, the specifics are not that important. It's just to demonstrate that there is a simple model to which we can translate from logic.
Well, these matrices actually are very important because when you learn the GNNs, that's what you're learning. You're learning the matrices.
Sure.
So if you tell machine learning person, oh, these matrices are not important, they will say, no, the matrices are the essence.
Yeah, I fully agree with their view. But here, I'm just going to do descriptive complexity. I don't care about learning.
Yeah.
Yes. But that's true. All right. Some questions. In which order do we sum over the neighbors' feature vectors? A typical solution would be to use some intrinsic parameters from the input graph. Maybe the domain is somehow implicitly ordered, and we would simply sum in that order.
Understand. As far as I remember, sum was commutative.
Sum is not associative when it comes to floating points.
Floating points. Oh, okay.
And that's kind of annoying. But if you take floating points seriously, as we do here, sum is not associative, so the order matters. If you just do this, if you just allow the sums in relation to some implicit order, then you go isomorphism non-invariant. So it won't be isomorphism invariant anymore. That's bad, because you must be isomorphism invariant.
But do you really want for your descriptive complexity, is floating point important for your descriptive complexity? Practically, of course, you're going to use floating point, okay?
Mm-hmm.
Well, you could use what's called infinite precision, but it's just very expensive, so nobody does. Everybody uses floating point.
Mm.
But we have the same issue if we just solve the linear equations, right? We have Gaussian elimination, and it tells you that the order of the rows and columns doesn't matter.
Mm-hmm.
But of course, as soon as you put floating point, of course, the order does matter.
Yes, yes.
But if you're doing descriptive complexity, why are you going from reals to float?
Well, why not? It's a more realistic model.
You're doing logic.
Yeah.
You don't care about the matrices, but you care about floats.
I don't know what to say, but I think this is pretty much the right approach to model this. If you really look into the details, you have to take into account things like this. I think this is largely just ignored. But it's not strictly speaking isomorphism invariant if you look at the
No, it's not.
Yeah.
But the same thing with many things that we tell students.
Yeah.
You do Gaussian elimination. Tell them the order of the rows and the column doesn't matter. Well, that's true for real numbers. It's not true for floating point. Okay.
Yeah, sure.
But the learning converges upon may depend on how the floats are operating.
Yeah. Sure. Anyway, we can sum in the order of the floats, and this is a common solution in numerical analysis. It also makes sure that the rounding errors are small. So this is a pretty realistic thing to do. So we are summing in the order of the floats. Right. So floats are obviously distributed in an uneven way over their domain. And this is important because you want to have a lot of floats close to zero, for example. They are very dense there and they are less dense elsewhere. And if you think of one of these floats close to zero, if you start adding it to itself, ultimately you are going to go out of the dense region. This means that no matter how many times you add it, you are going to be rounded back to the dense region. So these funny things happen with floats. So here's a theorem. These have the same expressive power, GNNFs and simple GNFs and GMSC. So this is the MSC where we have counting diamonds. So modal substitution calculus, but this time we have gradient modal logic under the hood. So diamonds can say that there are at least k neighbors that satisfy a certain property.
Remind us what simple means.
Simple was this terrible definition from here. This means not simple at all, in a sense.
Okay.
At least the definition is not simple. Yeah. Right. So this is pretty good. Notice that there is no background logic now. So this characterization is actually without limiting to some background logic. So we are not limiting to first order definable properties or anything like that. This is just absolute. Oh, that's nice.
For your combination function, and there was this other function with any strange thing.
Yes, yes. Actually, yeah. In the float case, it can be any, absolutely any. But ultimately, there are finitely many floats. So yeah. Right. Some words about the proof. Yes.
What is the connection between the substitution calculus and the neural network model? I mean, because in the neural network, you have real or floating point values. So you mean that you also have to extend the logic with predicates on reals or floating points, or?
I mean, the connection is here, I guess, in this theorem, isn't it?
Yeah, but I'm not sure how. I mean, how can you use the logic to express properties of the neural networks?
Well, or you mean properties of inputs to the neural networks, the graphs, right?
No, I'm not sure how you can compare the expressive power of the two things. That's my problem.
I mean, both of them take as input distributed networks, in a sense, or graphs, if you like. Oh, that's the wrong direction. So the inputs to both computing device classes are just models like this.
But also this equivalence holds because you are considering floating point numbers and not reals.
Yeah, one could say that there's this kind of a causality going on, but I'm going to say something about reals in a second as well.
Okay.
Yeah. A few words about the proofs. Note that every GMSC programmer has kind of a counting threshold because there's a maximum k that appears in the diamonds. On the other hand, the input graphs have unbounded degree, so you can put as inputs graphs of any size. So you might be puzzled, how is it possible that GMC is going to do the job in that case? And the key is that sum over multi-sets of floats have this following property. So there is an L, like a threshold number, such that if some float occurs in a multi-set at least L times, then we can change its multiplicity. As long as we keep it above L, we are going to get the same sum. This is related to the distribution of floats over the domain. All right, so GNNs without restrictions are equi-expressive with infinite disjunctions of formulas of, yes. Well, overflow is just, in the most basic models, it's just going to keep repeating the greatest float.
That's not what happens on a computer, right?
Well, yeah, but it's what happens in these floating systems. And you might hope that you won't actually reach overflow. But this convergence property here is not related to overflow. So, well, it's related, but it's not the same thing. So even if you look at the most dense area around zero, and you keep adding one of those floats to itself, you will ultimately reach the edge of that dense area. And then you'll be rounded back to that dense area, no matter how long, how many times you repeat this sum. It doesn't mean overflow. All right, so without restrictions, we get this really expressive model. Just infinite disjunctions. They don't have to be computable, anything like this. Right. Okay. But now, maybe a more interesting result. So in restriction to MSO definable node properties, all of these have the same expressive power. So GNNs without limitations and these floating point models. So this means that as long as you restrict to MSO definable properties, this is kind of okay. This difference between more realistic and theoretical models. There's no difference. All right, I can't prove this now for the time constraints. Yes.
So if you, let's supply yourself with very general definition of GNN.
Yes.
You can go to simple, which are very simple. So you can have crazy functions, and you can always simulate them by linear aggregation and ReLU.
Yes, I guess it's intuition is, well, it's hard to say. I mean, I think that everything relates to the fact that if you use MSO as a kind of background logic.
MSO. Oh, I'm just looking at the first two bullets.
All right, here.
From very general GNN with completely crazy coordination functions,
yes,
an aggregation function, you can go to very simple aggregation coordination function.
Right. Okay.
What's the magic there?
Yes. Well, I guess it would be easiest to define the intuition in some way if we use the Heaviside aggregation function. It simply says whether you are, well, you know what it looks like. It's kind of almost like a Boolean test. So this ReLU that we are using here is, we use it as a Boolean test, and therefore, because the number of floats is ultimately finite, we can simulate.
It's the key is the float. This will not be true if you go working with real numbers.
That's right. Okay. At least not in exactly the same way, but something like that is true anyway, because we get this result.
No, but now we're talking MSO definable.
Well, okay. Sure. Yes.
Yeah.
But okay. That's a lot of properties.
Yeah. Okay.
Yes.
Maybe just a quick question. Do you So what I know is that when you do recurrent neural networks, you usually use sigmoid. I've never seen any ReLU there.
Right. So this we simply take from the Paracelsus model. That's the simple GNN-F. But in GNN-Fs without this word simple, you can use whatever.
But also with float, right?
Yes. I mean, F here means floats. That's why I put it there. Maybe I'll skip the proof. There are some ingredients that resemble building bottom-up tree automata in MSO in this proof, but there are many other features, so let me not say more about that. All right. One note. Notice that the acceptance condition that we gave for graph neural networks in general, whether with floats or not, this can be varied. I mean, I don't think there is a standard accepting condition for recurrent graph neural networks. But the characterizations will simply hold. We just need to put the same acceptance condition on the logic. So what we are really modeling here is not only acceptance, but the actual computation. But this would require too much overhead for me to go through. So, all right. So I promised to say something about the semantic game for GMC. Why? Well, it's a path towards defining model comparison games, so Ehrenfreud Fraser games. When you have the semantic game, it's usually not very difficult to define a model comparison game, and that's key to expressive power. All right, so a semantic game for GMSC. This is kind of simple, and it does what you would expect it to do. It's meant to be used to check if a program is true at a node, and it's played between Eloise and Abelard. So intuitively, Eloise is trying to prove the formula, and Abelard is opposing this. So it's kind of a debate between the two players. This is specific to a program of TMC. Yeah. Of course, if you go to model comparison games, you need to get rid of the actual programs, but it's usually not very, very difficult. So the game here begins with Eloise choosing a number, and this is intuitively going to be the number of recursive iterations of the formulas. And this determines a beginning position that looks like this. So here, phi is the body of the induction rule for the appointed flag variable x1. If k happens to be 0, it's actually the body of the base rule. And after that, positions are of this type, where this v is either Eloise or Abelard, and it tells you who is the current verifier. And the other player is then called the falsifier. Then psi is a subformula of the body of some rule in the program. U is the current node, and L is just a number that tells you how many times you are going to be unraveling the recursion in the remaining game. So intuitively, you can read a position as follows. The player V can verify psi at the node U in L cycles of recursion. All right, so ultimately, if you end up in a position where you have a proposition symbol as your formula, the game ends. And the verifier wins if and only if the current node satisfies that proposition symbol. So it belongs to the extension of that proposition symbol. Otherwise, the falsifier wins. And if you meet a negation along the way, the current verifier becomes the falsifier. So if Eloise happens to be the verifier, from there on, Eloise is going to be the falsifier. So change of roles. Then evaluating a conjunction, the falsifier obviously chooses a potential counterexample, so a conjunct, and then the game continues with that conjunct. Graded diamond. The verifier chooses a set of k nodes, and these are distinct out neighbors of the current node. The falsifier chooses one node from that set, and the game continues from there. If the verifier cannot do that, so there are no k out neighbors, then the falsifier wins immediately. And then a variable, if L is greater than 0, the game continues from the position shown here, where we simply jump back to the body of the induction rule of this variable. And if L happens to be 1, then we jump into the base rule, right? All right, and having a winning strategy in this game is basically then just equivalent to the program being true in the usual sense that we defined it earlier. Now, this is not necessarily very surprising, but I think very interesting variants arise. For example, if you don't allow this number L here, if you simply just keep playing, it gives rise to some kind of a weird asynchronous variant that I don't even know how to define it as a rule-based logic. Right. Then I was going to say something about ordinary neural networks, but maybe for time constraints, I'm going to skip that. The message is that if you take the diamond-free graded model substitution calculus, so it's not model anymore, it's just some kind of an iterated Boolean network calculus, you can nicely characterize ordinary neural networks with that. So there's not much of a blow-up in the size and the so-called time delays in modeling the computation of the network. And this holds also for recurrent neural networks. But if you're interested in this, I can talk about that offline. A nice corollary to these results means that NNs can be translated with a modest blow-up to equivalent NNs with a ReLU activation function. All this is related to the world where we use floats. Thanks.
You go back to the last theorem about neural nets. But now you're running neural nets on what? What's the input? What is now the input to the neural net?
Just a string of floats here.
Just,
yeah.
I mean, before that, you define the formalism on graphs. Now, until now, you talk about input was a graph, was a label graph.
Yes, here it's not. Here it's not. This is not the graph neural networks anymore.
So what is the input? What is the program running on? The GSMC program runs on graphs, right?
Yes.
Define the semantics on cube structure.
The diamond-free is simply running on an assignment.
On
an assignment. A Boolean
just
assignment.
start with an assignment. Okay, because you don't need the graph structure because you don't have diamond.
Yeah.
Okay.
Yeah.
Okay.
Yes.
Other questions? Okay, so we're perfectly on time for the coffee break. Thank you very much.
Thank you.